Hey everyone. So, so this is the third talk of the Dead Case Theory seminar. So this time I'm pleased to have Logan Hyslop from UCLA. Logan will be telling us about twisted complex K theory. So Logan, please take it away.
All right, thank you. So today we're going to talk about twisted complex K theory. This is going to be following Atiyah-Segal's paper, Twisted K theory, the first 4 sections. Okay, so let's start with some motivation. So we're going to talk a little bit about what twistings are and where they sort of come from. So a classical case where you might see these is recall that if X is a compact oriented manifold, then we have the Poincare duality pairing. From the cohomology with Z coefficients tensored with itself. Well, you're taking n minus p, I should say n manifold, with Z coefficients. And you're going to map this by the cup product to the top dimensional cohomology class, and then map it over to Z. And this forms a perfect pairing, as we know from elementary differential topology. Now, if X is not oriented, then we can still do Poincare duality, except this second factor has to be replaced. We have to replace Z by a system of local coefficients. So that our duality becomes hv of x with coefficients in Z, answered with hn minus p of x with coefficients in this orientation sort of cover. And we're going to map by the cup product to hn of x with these local coefficients. And then we're going to map over to Z. Okay. So this is sort of the first place we really see twisting appearing, and in a sense, it's accounting for the fact that X is not nice enough in order to still do Poincare duality. We just have to change the coefficients to make them a little bit less nice, since X is a little bit less nice. Now, the start of our story today is going to be Poincare duality for complex K theory. Now, in this case, even when X is very nice, we have to introduce some twisting. So the key example that is given in Atiyah-Segal is you're going to take X, some compact Riemannian manifold, and there's going to be a bundle C over X, where the fiber over any point X is the Clifford algebra defined using our Riemannian metric on the tangent space, or the cotangent space rather, at X over the complex numbers. Okay, so using this bundle, this is going to turn out to be some sort of projective bundle, which will be defined shortly. And this is going to allow one to define twisted K theory with the coefficients denoted Kc of x. And this will take the place of our twisted coefficients of ordinary cohomology when doing Poincare duality. But this raises the question to what is this Kc of x? So let's start with a moral definition. Kc of x is the isoclasses of C modules over x made into a group by the usual Grothendieck construction. So you have to be a little bit careful what you mean by this. And this is what's going to sort of, this is the definition to sort of be in our back of our mind as we're doing general twistings of complex K theory in the sense of Atiyah-Segal. So without further ado, let's get into defining what is section 2 of Atiyah-Segal. My section numbers are going to follow their paper. Projective bundles. Okay. So when we want to do these twistings, for instance, for Clifford algebra before, we might want to allow some more general things to show up. We might want to, in particular, allow some infinite dimensional sort of vector bundles to show up when we're doing these sort of twistings. So explicitly, what we're going to do is we're going to start with a Hilbert space H, possibly infinite dimensional. And we want it to be separable. So we call from analysis that this means that there's a dense countable subset. Okay. So starting with some Hilbert space H, we can define the projective space of H as usual, just the usual project construction applied to some vector space. And this is going to lead into our next definition. So let X be a, say, manifold, or really just finite CW complex, locally compact Hausdorff space, what have you. A projective bundle P to X is a bundle locally isomorphic to U times the Hilbert space on some HU. So H is some Hilbert space on U, mapping down by the projection down to U. Here, HU, this Hilbert space is allowed to depend on U. A projective bundle with involution I guess just say projective space bundle is probably a little bit better. So that it doesn't get as confused with the notion of projective bundle in algebraic geometry. Projective space bundle with involution is a projective bundle P to X is a projective space bundle. Together with the decomposition of P plus and P minus. These are two sub-bundles such that locally P is the join of P plus and P minus. And we have that this is arising from some closed embedding for H into H prime. So this is going to be P plus is equal to the projective space of some sub-Hilbert space H, which is sits in a closed embedding into H prime. So P of H prime is equal to Px here. Okay. And what's some operators switching these two? Now what we're going to show is we're going to describe the set of projective space bundles over X. We can look at this and we're going to describe under some operation of taking tensor products, where you look at the projective space associated with the tensor product of two underlying Hilbert spaces, which is in fact well defined. You can also look at duals. So we have the same sort of things you would expect for vector bundles. And what we can do is we can impose this relation that the dual of P is equal to, let's see, minus P. And we're going to get some group here, proj bundle 0 of X. Which is going to turn into a group under this tensor product operation. Taking the dual is sort of the naive thing you would think of when you try and think of vector bundles. Okay, so now here's the theorem from Atiyah-Segal. This is their proposition 2.1. There is a group isomorphism called eta here from proj bundle 0 of X, mapping to degree 3 cohomology with coefficients in Z. If E is infinite dimensional and separable, it is determined up to isomorphism by eta P and its structure group. If a class here is torsion, then it is represented by a finite dimensional projective space bundle P. And conversely, if P is finite dimensional, then the class of P is n torsion. It could be torsion for some m dividing n, but in particular, you can show that it is n torsion itself. And this is sort of giving you a full description of the projective space bundles over X in terms of this third cohomology. So let's prove this. So first we need to construct the eta. We can choose a suitably fine open cover UI of X. And on here, we're going to have our Hilbert spaces P of HI, UI times this. And we're going to have our restrictions Uij times P of HI, mapping to Uij, Uij meaning the intersection, times P of Hj, given by some rho ij. Now, rho ij can be assumed to come from a map from hi to hj, which is determined up to a constant factor. The way you prove this is if you're finite dimensional, then you can just look at an orthonormal basis of hi and see where this goes such that it induces the same map on the projective spaces. If you're infinite dimensional, then there's a so-called orthonormal basis of the Hilbert space, which means a linearly independent set such that the inner product of any two elements, ei and ej, is the Dirac delta of ij. And then what you note from this, and that this is dense. This generates a dense subspace. You don't require that it spans the whole space because you can't really get this with the Hilbert space in general. You just require it to be dense. After you have this for hi, you can figure out where this orthonormal basis goes on hj by a similar procedure in order to induce the same map on the projective spaces. By completeness, this extends to a full map from hi to hj, which is then an isomorphism, which induces the desired map. Okay. So in particular, we have our co-cycle condition, which is that our PHI going to PHJ and then PHK. Those are rho IJ, rho JK, and here we're going to have rho IK. And we need this to commute. So we need that rho IK inverse times rho JK of rho IJ is equal to the identity on HI here. So in particular, this full composite is going to be the identity on the projective space. So you can get that it's induced from, if you treat these rho IK inverse rho JK, rho IJ, these maps here are going to take our UIJK, our intersection, to the circle, given by the difference between the actual way you compose these and the identity, which is off by some constant scalar. So this is going to determine a cocycle, giving us a class, or rather, I guess what's better to say is, yeah. So these maps here are giving us some cocycle, which we're going to call eta associated to P, which is going to live in H2 of X with coefficients in the sheaf of, this here is the sheaf of continuous functions to the circle. And we have the short exact sequence coming from the exponential exact sequence. So we have the constant sheaf on Z, so this is continuous maps from X to Z. This maps to continuous maps from X to R. So here, this is equal to continuous maps from dash to z, from open x op to set. Well, really, I guess I should say in groups. And this is now to this sheaf here. So we have this short exact sequence of sheaves. This is going to lead to the long exact cohomology sequence. This here is equivalently the constant sheaf on Z. This here is not the same as the constant sheaf on R because we're considering R with its topology. So this is sheaves on R here, which this is like one of the special kinds of sheaves that I always forget the name of. If it's not flat, it's a soft sheaf, which means that its higher cohomology vanishes. So in our long exact cohomology sequence, we have H0 of xz to H0 of xr, well, sheaves on R, to H0 of x sheaves on T, H1 of xz to 0 to H1 on x with sheaves on T, H2 xz, and here we get our term that we wanted, H2 of x with coefficients and sheaves on T, which maps isomorphically to H3 on x with coefficients in Z. And this here is where we wanted eta p to live. And since this is isomorphic to this, the cocycle we constructed gives us exactly the class that we want. So this gives us a map one way, which is not a priori a group homomorphism, but we're going to describe this in a few other ways, which is going to end up giving the thing. Okay, now we're going to construct an inverse data. Okay, so if we start with some projected bundle p to x, then the structure group, if this is locally, the projected bundle on some liquid space H is going to be given by the unitary group on H here. So we can assume that without loss of generality, P is infinite dimensional. Since if you're in a finite dimensional case, you can always find a class in this, you can always find some P in the same class in project bundle 0 just by multiplying by n to P for P some big infinite dimensional Hilbert space, which is going to go to 0 in this group here. So you're just adding an identity element to get it to be infinite dimensional. Okay, so without loss of generality, P is infinite dimensional. So in particular, this here is contractible in the compact open topology. And it has a free circle action. So when we quotient to the projected unitary group, this is going to just give us a model for the classifying space of the circle. I guess I should say homotopy equivalence, it's better, which is the classifying space of a KZ1, which is a KZ2. So when we're going to look at the classifying space for these projected bundles with this structure group, we're going to look at BPU of H, which is going to be BK of Z2, which is a K of Z3. Eilenberg-MacLane spectrum, Eilenberg-MacLane space K of Z3. So any map from X to K of Z3 up to homotopy. So any homotopy class F here, which is going to be giving rise to a class equivalent to a class here in H3 of XZ by representability of cohomology. This is the same thing as giving a map to, or rather a homotopy class of maps to be Bu of H, this classifying space for these bundles. So we can take the universal bundle over here, and we can pull it back to X. And one can check that eta of P of F is equal to the cohomology class F. So this gives an equivalent way to describe the map from before. Okay. Now, if we have our projective bundle comes from something finite, so like P to the NC, then this arises from this sort of short exact sequence of, rather this commutative diagram of fiber sequences, I should say. We have something like this, mapping here to UN. And here we have the circle acting on it. And then if you apply the classifying space construction to all of these, then you get that the map, that the class we want in BT is going to factor over being UN. And in particular, we see that it is going to be n torsion since it's coming from something in here, which is going to consist of n torsion points. Conversely, if P is a torsion class, a theorem of Serre says that the class here in B of the circle, well, I guess this guy here is B of the circle, if you work in fifth dimensional, at least. Okay, sorry, B of the circle, then this is going to come from, I should do two B's here. If you have a class here, which is torsion, then we're going to get that it is actually going to come from B of mu n, sort of a limit here, as n is increasing. So it's going to factor over something finite, but it might not, if it's n torsion, it might not come from a class here of order n. The torsion might show up somewhere else. Yeah, the way you sort of prove this is you sort of like look at sort of a limit of these sequences, and you're looking at dp u infinity and trying to look at the torsion phenomenon happening in here. Okay. And to see if this is actually a group homomorphism, you look at sort of these commutative diagrams like this. And then here you can map down by the multiplication. Here you can map down by taking the tensor product of matrices. And then finally you do the same thing over here. And sort of use naturality in representability to see that the maps induced on the classifying space of these last guys by first taking in F, then going in by G, and then applying this sum operation in the cohomology is going to be the same thing as starting with your bundles. First you tensor them, and then you go into here. Okay. That's a little bit of the sketch of how the proof works. So one other point that is somewhat important is a lemma. If P not going into P is a tame subbundle. So this by this we mean locally of the form U times the projective space over some Hilbert space H0, including into U times P of H, where H0, including into H, is the inclusion of a closed subspace. Then we have that their classes agree. And the proof of this uses a similar diagram to here. So for this one explicitly, is you look at the circle here with an isomorphism from itself going over to itself. Now on the top here, you're going to use the unitary group for H naught, and then this PU of H naught. Over here, what we're going to use is the unitary group for H, comma H naught, and the projective unitary group for H, comma H naught. And similarly on the bottom rows, we're going to use H. So what this middle group is U of H, H naught, is going to be the set of unitary matrices acting on our big Hilbert space H, such that M of H naught is equal to H naught. So it's going to also induce a unitary operator on this subspace here. So that's how we get this top projection up here. It's just by restriction, and this bottom projection is just forgetting. And since we have isomorphisms on our T's, this is going to give us exactly what we want in terms of showing that the two classes of P naught and P agree. Okay. And there's another corollary you can do, which says that you can describe the similar group Proj bundle 0 with involution of X. Now this one is going to be isomorphic to the degree 1 cohomology of X with Z mod 2 coefficients. So real line bundles. And this is going to sit in a semi-direct product with H3 of X coefficients in Z. Should go the other way. Right. And this semi-direct product acts by Z1, comma, eta 1, plus Z2, comma, eta 2. We're just going to have, of course, Z1 plus Z2. And now we're going to have eta 1 plus eta 2, plus this extra element beta of Z1 times Z2. So this here is our cup product. And beta is the Bach-Stein from H2 of X with Z mod 2 coefficients to H3 of X with Z coefficients. Okay, so why is this true? Here's the sketch. What you're looking at is you sort of split up by looking at two different line bundles for SL1. So some line bundle here, some line bundle tensored with some Hilbert space. And you're going to map to some other line bundle, tensor with some other line bundle, SL2, tensored with H. And if you have something like this, then this is isomorphic to the projective space on SL1, tensored SL2, tensored with H, tensored itself. And what you have here is this is going to give you L1 plus L2. The sort of line bundle you're twisting with is going to give you this, together with H itself, since H is isomorphic to H tensored itself. And now you sort of use the standard operations of what line bundles do by looking at their characteristic classes. This is a little bit sketchy, but that's sort of the main idea. Okay. Now for actually defining twisted complexity theory. Okay. So we go through a few iterations. So if H is an infinite dimensional Hilbert space, one can look at the space of Fredholm operators on H. So this is the space of operators A, such that there exists an operator B with AB minus 1 and BA minus 1 compact operators. So this is almost invertible operators, where by almost I mean up to a compact operator, such that the difference between A and being invertible is going to be given by something compact. Okay, so this with the norm topology, one can show that Fredholm H is a space representing complex K theory. So Ku naught of X is the homotopy classes of maps from X to Fredholm operators on H. So when we're constructing our twisted form, twisted K theory on X, which we're going to call Kp naught of X, we also want a similarly defined space. Okay. So if we have a bundle T to X, we can construct a new bundle of Fredholm operators on P mapping to X, where the fiber over any point X, which would have P of Hx, is the Fredholm operators on Hx. This Hx is not determined canonically, but this is. The idea for this is, as I sketched before, I'll give a sort of formal argument for it, is if we have an isomorphism of the projective spaces of Hilbert spaces like so, then this implies that there exists a unique up to a constant factor isomorphism, not necessarily isometry, from H to H tilde, which gives rise to this. So what we do is we take some orthonormal basis set EI is an order I of H. Let me also assume that these are separable, so that I is countable. Now we can take E1, which is going to represent, say, like 1 to 0 to dot dot dot, is what we might think of this as in P of H. This is going to map to some linear subspace in P of H tilde. So we can determine, just pick some arbitrary elements in this linear subspace, which is non-zero, E1 tilde in here. Now we can do a similar thing for En tilde, for Ei tilde, for I is normal of I. But we want to choose this coherently. So for instance, we want the subspace determined by E1 plus E2, or like EI, to map to the subspace of E1 tilde plus EI tilde. So we want to choose the scalar such that this does work out. And when we do this, we could determine a map from the span of our EIs, mapping over to H tilde, just the vector spaces on at the moment. Now this here sits densely in H, which maps up to here. So by density, we're going to get some extension up this way. All right. And now this extension is going to give us a map from P of H to P of H tilde. We can check that this here was already injective, which is going to agree on the subspace P of C to the I, which is sitting in here densely. So this is going to agree on this guy with our original map. And since this is dense, and their targets is Hausdorff, these two maps agree. Okay. So this shows that we have some isomorphism from H to H tilde, which is then unique up to the constant factor, giving rise to this map up here. So this is our claim. All right, so with this in mind, this isomorphism is going to give us a map from the endomorphisms of H to the endomorphisms of H tilde. Any other map that determines the same map on the projective space is going to determine something which is a conjugate of this by some scalar, so just the same as this map. So this map is unique up to canonical isomorphism, or rather, I guess this space here, end of H, is unique up to canonical isomorphism, I should say. This isomorphism here is canonical. So we can define end of P, Fredholm operators on P, whatever you want, some sort of operator such a space on P, and this is going to be canonically defined. Okay. So our sort of idea is we want to start with Fredholm operators on our bundle P. And we want K0P of X to be defined as sections of this bundle. So if P were some trivial bundle, like the projective space on some infantile space times X, then we're just asking for sections of X times Fredholm operators on H to, I should say Fred H actually is the bundle I want. We're looking at X times Fredholm operators on H, mapping down to X, so sections of this, which is just the same as homotopy classes of Fredholm. Let me specify homotopy classes, which is the same as maps from X to Fredholm operators in H, which, as we said above, is the same thing as K0 of X. The issue here is we defined the bundles P of H in terms of compact open. Apologies. So Fred H does not work so well. In the compact open topology, where it's now contractible. So in particular, it represents the point, which is not K0 of any space. In fact, there are spaces with non-trivial K0. So the solution is you're going to define a new bundle Fred prime of H. This is going to be a set of pairs A comma B. So here the idea is we're just remembering a pseudo inverse for A. So such that AB minus 1 is equal to compact. Same thing with BA minus 1. You're just remembering the data of this B. And this is topologized as a subspace of space of bounded operators times compact operators times compact operators, where this map is going to take A comma B and map it to A, B, AB minus 1, BA minus 1. And you give this subspace topology. In the proposition is that this space represents K-theory and works well for what we want. Okay. So by works well, I mean that we have a PGL of H action on this space. There's a few other constructions you can do for defining the actual operations, which you go through using projective bundles with resolution, with involution. That's very useful for trying to define the multiplicative structure. We're going to gloss over this a little bit and talk in the last few minutes here about algebraic K-theory and its connection to this, just very briefly. So classically, on a vector space, on a manifold X, we have that K0 of X is going to be isomorphic to the algebraic K-theory of the infinity functions on X. This sort of Banach algebra. This is discussed, for instance, in Weibull. I don't remember what chapter. It's probably chapter 1, maybe chapter 2, something like this. Okay. So we can ask if something similar holds here. The naive guess is we have something like take global sections of our Hilbert's sum of our Hilbert space bundle P of H or something. But similar to before, where we talked about inclusions of closed spaces, the corollary we had way up here actually shows that this lemma actually shows that if P has any global sections, then we're going to get a map from a sort of one-dimensional projective space over X to it. And that's going to give that its class is trivial. So that's not good. We don't expect this to happen in general. So this is not what is going to happen. Instead, we have this new bundle over X, where KP is going to be the compact endomorphisms of our bundle PX. And we can prove that K0P of X is the same thing as the algebraic K-theory of this ring of global sections of this bundle KP. All right, so a few useful remarks is that we have a map from KP0 tensor with KP prime 0 to K P tensor P prime 0 of X. So we have some compact operator here. Sorry, if we have like we're thinking like the Fredholm space, like Fred prime, for instance, if we have like A here and some A prime over here. I'm really thinking like Fred H secretly, but well, actually secretly I'm thinking Fred prime of H, but for simplicity, let's just say we're thinking Fred H and Fred H prime. We can map this to A tensor 1 plus 1 tensor A. Okay, you really want to be in Fred H prime prime for this to make that much sense, which is defined in their paper. So see section, it's probably section 4 of the Atiyah-Segal, where this is really constructed in more details. But the point is that this is going to give you some cohomology operations like so. And since we have this for all P and P prime, in particular, we can apply this for P is equal to the trivial case to get that K0 P of X is a K0 of X module for all P. Okay, and this is going to give us X comma P mapping to K star P of X. This can be defined into a cohomology theory on the category of pairs XP, where X is a, say, CW complex, and P to X is a projective space bundle. And because of this, you also get an Atiyah-Segal spectral sequence with E2 page, just the classical thing you would expect from an Atiyah-Segal spectral sequence. HQ of X is coefficients in KP of KP plus Q of X, converging to KP plus Q over this projective bundle of X. So the E2 page agrees with the E2 page for ordinary complex K theory of X. I guess it should say for the Atiyah-Segal spectral sequence for the ordinary complex K theory of X. But these may differ because the twisting is happening on the differentials. And possibly, I guess, on extensions. Okay. That's sort of all I have for today. We're just about at 2 o'clock, so I think I'll cut it off here. Marta, you there? Any questions?
Yeah, wait. Do you have questions? Wait, if not, let's take a speaker. And I can probably stop recording.